Let's look at some exam questions regarding the normal approximation to the Poisson distribution. The first of which is this one. This is a June 2005, paper 7, question 6. At a petrol station, cars arrive independently and at random times at constant average rates of 8 cars per hour traveling east and 5 cars per hour traveling west. Find the probability that in a quarter-hour period, first, one or more cars traveling east and one or more cars traveling west will arrive. Okay, the information that you are given is the number of the rates, the mean of the number of cars per hour in both situations, heading west and east. But the question that you have to solve regards a different interval, in this case a different time frame. This is based on quarter-hour periods. Okay, so we have to pay attention to these details. Looking at the question, you know the information that you are given is that headed east you had 8 cars per hour, headed west you have 5 cars per hour, so you have to adapt this to the new time frame, which is a quarter of an hour, 15 minutes. So heading east, basically you will have just 2 cars and per quarter minute intervals, and heading west 1.25. Okay, this is the parameters. These two are the parameters that you are going to use to calculate the probability. What probability again? Is the probability that you have, let me go there again, one or more cars traveling east and one or more cars traveling west. So you want the probability that you have that E being the number of cars traveling east is bigger or equal to 1, and W being the random variable, meaning the number corresponding to the number of cars heading west, being bigger or equal to 1. Multiply them together. Here you have the way to calculate it as usual. Use the formula that you have on the Poisson distribution, and just plug everything in a calculator, and that is going to be the result. B. Calculate the probability that in the same quarter-hour period you have a total of 2 or more cars arriving. Now, it doesn't matter if they come from the east or from the west. So in this case, we can set up a new random variable that is just going to be the sum of these two, all right? It really doesn't matter if it is coming from east or west, in which case you just have to add the means, the two parameters, previous parameters, and you'll have a new parameter of 3.25. As simple as that. And now you want the probability that t is bigger or equal to 2. So 1 minus the probability that t is equal to 0 and equal to 1. Again, just apply the formula using the new parameter, and there you have the result, the probability. Then you have find the approximate probability that in a 12-hour period, a total of more than 175 cars will arrive. Again, doesn't matter if it is from the east or from the west. So now what do you have? You have a 12-hour period, so the interval is also going to change. The same way that we calculated, we adapted the new mean for this smaller time frame. We have to adapt the mean for this bigger time frame. So this is going to be 12 times 8, that's 96 coming from the east in a 12-hour period. And from the west, do the same thing, and you have 60 cars. They are both bigger than 15. What is the relevance of that? Is that you can also use the you can use now the normal distribution as an approximation for the Poisson. Anyway, I just go ahead and represent the original distribution that can be used for both situations. But t, the total, the new random variable that is going to be corresponding to the sum of the cars coming from the east and the cars coming from the west, is also going to be represented by a Poisson distribution with parameter 156. Again, you just have to add these two, remember? So you add the two previous parameters, you have that one, and now, since this is also bigger than 15, you can use the normal approximation to the Poisson distribution. All right, so the parameter is going to be 156 for the mean and the variance. So the probability that t is bigger than 175 is 1 minus the probability that t is smaller or equal to 175. And then you just have to find the z value for this, okay? Obviously, this is smaller and equal, so you have to use the value 175.5, get the z value, and get the final probability. See the importance here of using this approximation? The alternative would be to continue using the Poisson distribution, but what would be the practicality of that approach? You would have to calculate it 175 times, right? You have to calculate it for t equal to 0, t equal to 1, t equals 2, etc. This is much simpler. This is why this approximation is used. Let's look at another question. This is also a paper 7 from June 2006, and the question is question 6 over here. A dressmaker makes dresses for easy fit fashions. Each dress requires 2.5 square meters of material. Faults occur randomly in the material at an average rate of 4.8 per 20 square meters. Just with that information, find the probability that the randomly chosen dress contains at least 2 faults. Okay, so what information are you given? As usual, I already expressed everything that is numerical over here. All right, so you have an average of 4.8 faults for every 20 square meters of material. So that gives an average of 0.24 faults per square meter of material. Now, one dress has a total area of 2.5 square meters. So what is the question again? What is the probability that a randomly chosen dress contains at least 2 faults? So we can set up a random variable corresponding to the number of faults in one dress, and we can use the Poisson distribution as long as we have an average to use for this. And what is the average? Is the product of the area of one dress by the probability of finding a fault per square meter. So 0.24 faults per square meter times the 2.5 square meters of one dress gives a total of 0.6 faults per dress. So we have here the mean, the parameter that we can use in the Poisson distribution. So right now it's just a matter of setting up the equation, the probability that x is bigger or equal to 2, and basically solve it, and there you have the answer. Then the question continues saying, each dress has a belt attached to it to make an outfit. Independently of faults in the material, the probability that a belt is faulty is 0.03. Find the probability that in an outfit, neither the dress nor its belt is faulty. For the belt, it's very simple, right? The probability that a belt is not faulty is 0.97, right? 1 minus that. We need to figure out now the probability that the dress is not faulty, and then multiply them together to get the final answer, right? So there you have it. The probability that the belt is not faulty is 0.97. The probability that the dress is okay, so neither one are faulty, is this one times the probability that x equals 0, right? So I just apply the formula and multiply by 0.97, and that's the answer. Simple enough. Now, next one is probability that the dress that in an outfit, the dress has at least one fault and its belt is faulty. So again, the probability that the belt is faulty, definitely, and at least one fault is found on the dress. So again, this should be obvious already. This is the probability that x is bigger or equal to 1 times the probability that the belt is faulty. All right? So there you have it. The usual way to calculate it, just substitute, and there you have the result. This is going to be important for the next question, as you're going to see. The dressmaker attaches 300 randomly chosen belts to 300 randomly chosen dresses. An outfit in which the dress has at least one fault and its belt is faulty is rejected. Okay, so these are the conditions that you just calculated before. Faulty belt and at least one fault in the dress. Now, use a suitable approximation to find the probability that fewer than 3 outfits are rejected. Okay, so you have a total of 300 dresses, okay? The probability that the dress has at least one fault and the belt is faulty, you just calculated before. I'm just adding here one significant figure because this is an intermediate value that you are going to use to get something else, all right? And now they are talking about a suitable approximation. What approximation is this? I put this on purpose. This is not going to be the normal approximation to the Poisson distribution. What you are going to use here, because the nature of this is a binomial distribution, either this happens or not, but you have here the product of NP, N being the sample, which is 300 dress, and P the probability, and P is going to be 4 point something, which is smaller than 5. So what approximation are you going to use? You use the Poisson approximation to the binomial distribution. I put this here on purpose because on an exam you are not going to be told which approximation to use. So although this set of exam questions were supposed to be focusing on the normal approximation to the Poisson distribution, I put this here on purpose. This question could be on the previous lesson when we talked about this, but I put here on purpose for you to be aware of the fact that in an exam, they don't specifically tell you what approximation to use, all right? So in this case, again, it's something that you learned in the previous lesson. The product NP is going to be the parameter that you are going to use in the Poisson distribution. So that's 4.062 in this case. And you want a probability that X is smaller than 3. You have less than 3 dresses with that problem. So now that you have the parameter, it's as simple as setting up the equation, substituting the values, and getting the final result. I promise that the last example is going to use the normal approximation again, but usually this comes as a secondary or one of the sub-questions in a main question. In this case, it's a paper 7, June 2007, and it's question 5 again. Let me just make sure of what I'm saying. I have this written over here. No, it's question 5, yes. It is proposed to model the number of people per hour calling a car breakdown service between the times 9 and 12, 9 a.m. and 12 and 9 p.m. By a Poisson distribution. Explain why a Poisson distribution may be appropriate for this situation. So if you remember, the conditions for you to use the Poisson distribution involved the number of the events being equally distributed. So in this case, the events are the number of calls. They are supposed to be uniformly distributed in this time interval. And also the events are independent of each other. So the other condition is that the calls are random and independent of each other. You have here a total of 3 different things. The question had 2 points. So I'm guessing that if you get any 2 of these correct, you'll have the full credit. The question continues with people call the car breakdown service at an average rate of 20 per hour. And the Poisson distribution may be assumed to be a suitable model. So You are told about what distribution to use. It's the Poisson. Find the probability that exactly 8 people call in this half an hour. Okay? Now pay attention to the time intervals as well. The question is giving you the information in terms of calls per hour. So the time interval is 1 hour. But the question is focusing on periods of half an hour. So it's important that you establish your parameter in terms of the interval the question is mentioning. So this would be obviously 10 calls per half an hour intervals. X is going to be the number of calls in every half an hour, and is going to be modeled by the Poisson distribution with parameter 10. You want a probability that X equals 8, so just apply the formula and there you have it. The difficulty here was for you to pay attention in this, okay? This is extremely important, and then sometimes, like in this case, the intervals are going to change, so you'll have to adapt the information, the mean that you are given in the beginning of the question, to the new intervals. Let's see. We are here. By using a suitable approximation, find the probability that exactly 250 people call in the 12 hours between 9 a.m. and 9 p.m. Okay? So now you have to use the approximation. I already told you that this is the normal approximation to the binomial, and let's see why. If you have 20 calls per hour, in a period of 12 hours, you'll have a total of 240 calls, right? If X is a number of calls in the 12 hours, that's how the question is made, then X can be modeled by the Poisson with parameter 240. This is bigger. This is a bigger number, so the Poisson can be used. So the normal distribution can be used with parameter 240. So this is going to be the mean as well as the variance. So you just go ahead and if you want to calculate the probability that X is 250, this is obviously done by getting the Z value using the 250.5 value first, and then the Z value using the 249.5 value after, doing the difference between these two. Get the two Z values, go to the MF19, find the probabilities for each one, subtract, and there you have the answer.